The purpose of in-service tests is to check the protection schemes under operating conditions, and that is with the primary equipment energized and on load. Energizing the primary equipment is usually the responsibility of one designated commissioning engineer, assisted by the operating personnel, the protection personnel, and other departments. Before energizing, they will make sure that all work has been completed, that all temporary grounds are removed, and that all permits to work are cleared. All protection relays should be in service, even though further adjustments may have to be made. Indeed, for the first energization, the protective relays may sometimes be temporarily set to give increased sensitivity. Before any primary equipment is connected into the existing power system, the phasing must be proved. In most installations, the primary circuitry is exposed so that a visual inspection can be made to ensure that the primary phasing is correct. That is, to make sure, for example, that the A phase of the bus is connected through the A phase circuit breaker and disconnects to the A phase of the transmission line. Similarly with the B and C phases. However, this visual inspection is not always possible. For example, a three-phase transformer has internal connections. Also remember, there will be a phase shift between primary and secondary for a Y-delta connection. In most cases, phasing of the transformer would have been tested during installation by applying a low voltage, say 600 volts, to the high voltage side and measuring voltages on the secondary. Plotting the resultant phasor diagram will prove the voltage ratio, phasing, the phase shift, and phase rotation. For voltages up to, say, 25 kV, phasing checks can be carried out by using insulated phasing sticks. These can be inserted into energized switchgear spouts or across open disconnects to check the voltage across the break for each phase. If phasing is correct, the voltage across the open contacts should be 0 or close to 0. However, if phase rotation is incorrect, a high voltage will appear across two of the phases. A typical list of general instructions for initial energization is included in your workbook. Let's consider an example of synchronizing a new generator to an existing bus which is energized. The generator is run up to speed and excited so as to provide the required test voltage, probably lower than nominal. This will apply voltage to the windings of both the unit step-up transformer and unit auxiliary transformer. Remember, both unit and auxiliary breakers remain open. The first task is to test the VTs which are connected to the generator terminals. Compare the secondary voltage to a known source to ensure it has correct phasing and phase rotation. Many VTs are fitted with a tertiary winding, which is connected in broken delta. Check this voltage. It should measure 0 or very low voltage. At this point, the generator terminal voltage can be raised to nominal value and voltage tests carried out on all protective relays. Clearly, before paralleling the new generator to the existing bus, we must ensure that phasing and phase rotation are identical on both sides. This may be done on the high voltage side of the unit transformer. Another method is to shut down the generator, open the terminal links, and backfeed the VTs by energizing the unit transformer from the high voltage side. Compare VT phasing and sequence to a known voltage, and with readings taken with the generator energizing the VTs. It's most important to make sure that the synchroscope is receiving correct information. It must be connected correctly to the VTs on either side. Remember, there will probably be a phase shift across the unit transformer, and this will have to be taken into account by the synchroscope connections. Once the generator is paralleled to the bus, load on the turbine generator can be raised sufficient to give adequate current readings on the CT secondaries, and so allow in-service readings to be taken at the CT links. As an example, let's look at in-service readings of the generator differential protection taken at the relay panel. Our objective is to test the magnitude and phase angle of current in each of the restraining coils and operating coils. A suitable ammeter and phase angle meter are connected to the circuit under test through the test board. The phase angle meter must be provided with a fixed voltage which can be used as reference in order to determine the phase angle and consequent direction of current. With a balanced load on the generator, the current passing through each relay operating coil should be at 0 or a very low value. On the other hand, current measured through the restraint coils should be equal to the CT secondary value. In any particular phase, the current through the restraint coils on either side should be 180 degrees apart. The current enters at one relay terminal and exits from the other. This is correct if there is no internal fault. If the test shows different phase angle relationships, then the CTs have been incorrectly connected. However, this problem should have been discovered earlier by secondary or primary injection tests. Transformer differential protection can be measured in a similar manner. But in this case, we should expect to see some current passing through the operating coil. As we pointed out in an earlier videotape, this error current or spill current is due primarily to the selection of transformer taps, plus the effect of dissimilar CTs on either side of the transformer. Obviously, the ratio of spill current to restraint current as measured during the test should be lower than the differential setting of the relay. As soon as possible, with load on the generator, the corresponding bus protection CTs must be checked for balance and secondary current magnitude and direction. When this test is completed, we should check at the protection relay panel that the summation of all the bus CTs is 0 or very close to 0. When a transmission line or feeder is energized from one end only, charging current will flow to feed the natural capacitance of the line. This may be sufficient to allow us to perform a preliminary check of the current balance in the CT secondaries. Preferably, a radial load should be connected at the far end of the line. In this manner, we can be absolutely sure of the direction of current flow when taking in-service readings. In order to check pilot protection, we need to take in-service readings at each end of the line by measuring the value of secondary current flowing in the operating coils and restraint coils. With a phase comparison scheme like this, we would expect to find 0 or very low current flowing in the relays and pilot wires. This would indicate that the CTs are correctly balanced. We can simulate a through fault, say a ground fault on phase A, by disconnecting the CT connections to phase B and C, not forgetting to place a short across the CTs. This is usually done at the test plug board like this. With this arrangement, we should have considerable current flowing through both restraint coils and the pilot wires. Current through the operating coil should be 0 or close to 0. However, if the relays at both ends operate incorrectly, then the pilot wire connections should be reversed at one end only and the test repeated. In many power companies, the standard test procedures indicate that for this type of test, the output tripping signal must be blocked. Of course, relay output to alarms, auxiliary relays, and other devices must remain. Moreover, this isolation is only permitted where sufficient residual protection and backup protection is available. Remember, duplicate protection is usually provided on important circuits. Great care must be taken in carrying out service checks on directional relays. Where voltage polarization is used, the voltage balance and phase sequence of the secondary voltages applied to the relay should be thoroughly checked as soon as the VTs are energized. Make sure that the connections agree with the wiring diagrams and the manufacturer's manual. For example, the A-phase directional relay may require voltage polarization from the B and C VTs. This is to provide the desired directional control. You'll remember we discussed this in earlier videotapes, specifically 2 and 9. To check the phase relay, the load current magnitude, direction, and power factor must be measured accurately. Also, the value of current and its phase angle provided to the phase A directional relay. The phase angle meter should use as a reference voltage the A phase to neutral VAN. If a phase angle meter is not available, a watt meter could be used with its voltage coil connected phase A to neutral. We must also accurately measure the voltage input to the relay and its phase angle relative to VAN. This will enable us to draw a phasor diagram indicating the relative phase displacements of current, IA, and the polarizing voltage. With current flowing in the designated tripping direction, usually into the line, the directional element contact should operate. This will act as a permissive to the overcurrent or other protective element. So tripping should not occur under normal operating conditions. To check the blocking element of the directional relay, we can simply reverse the flow of current to the relay by cross-connecting the CT connections at the test plug. In this situation, the directional element contacts should open. Before conducting any in-service tests, be sure to discuss the activity with the operators and alert them to possible inadvertent tripping. This will allow them to prepare contingency plans. Incidentally, when performing in-service checks, the sequence of events recorder should be in operation to help analyze any incidents. So we have looked here at just a few examples of in-service tests. Enough, I hope, to get us all thinking and to realize the excellent opportunity that these tests provide for checking out the complete protection schemes. Your utility company should have complete, detailed procedures for all in-service tests to be conducted on your specific protection schemes. Make sure you study this material and check any problem areas with your supervisor. I'm sure you'll find a few. When carrying out commissioning tests, remember that you are part of the overall commissioning team. All drawings should be marked up to show the actual as-built condition, including modifications made during the commissioning tests. These must be passed on to the appropriate engineering department. Also, inform the operators of any changes and any other pertinent information. Good communication and coordination is absolutely vital, and especially pay attention to safety procedures at all times.